All right, we're getting started here this afternoon. Good afternoon, everybody. Thank you for attending our webinar on grounding foundations. This webinar will be with Jerry Callison. Jerry Callison is a electrical engineer here at Commonwealth. His background is that he's been working in substation for quite some time, over 15 years, and is our subject matter expert in system grounding. Jerry is a PE as well and licensed in Michigan. He holds a BSEE from University of Wisconsin-Milwaukee and an MSEE from University of Tennessee. He's also a member of the IEEE Power and Energy Society, and he is on the IEEE Substations Committee working groups, particularly on auxiliary systems and substation grounding. So looking forward to working with Jerry today. Head to the next slide here. So just before we begin, a couple of other introductions. My name is Ian Hutt. I'm the Associate Director of Engineering for Power System Studies at Commonwealth and been working in the industry on power system studies and related grounding topics for almost 20 years. For those that are looking to get PDH certificates, note the email here. It's marketing@cai-engr.com. If you send a message with the subject line grounding PDH, we'll work with you to get you your PDHs for this discussion. So thank you for that. The webinar recording will be available after the presentation is over. We will post that to all attendees. And also, just a little plug for our next webinar in about a month, November 20th. We have another station webinar that's going to be substation installation coordination. Another hot topic and an area that we handle here in our Power System Studies group at Commonwealth. So I hope you're able to attend next webinar as well, and another PDH will be available then as well too. All right, that being said, I'll hand this over to Jerry. Jerry, take it away.
Well, thank you, Ian. Like Ian said, my name's Jerry Callison, and I am the grounding SME among other hats that I wear at Commonwealth Associates. And in my role doing grounding for Commonwealth projects, sometimes I have to send out a very unhappy message that the grounding, that the soil measurements that we had planned on, we'd been provided to do our grounding design based off of are not good. And that's definitely not a message that you want to get, when you're expecting a grounding design in a matter of a few weeks that you have to go back and retake measurements. So if anything, I'm really hoping that this talk today can, educate people how to take good measurements for grounding and how to avoid that situation in the last minute you find out that you need to take, retake measurements for soil resistivity for grounding. So on that note, we'll talk about the outline of my presentation. We'll talk about background in soil modeling first. Then we're going to talk about how to pick good Wenner 4-pin traces. And then we're going to talk about the soil reports, the anatomy, things to look for, how do we judge these resistivity results once we have them. We're going to talk about a couple of lessons learned. One I talk about called recently mulched. Another I talk about inadequate probe depth. And then finally, we're going to talk about, we'll have questions and discussions. So with that, have a safety minute. And this is kind of an easy thing to do when you're talking about grounding, because grounding is all about safety. And so what better thing to talk about for a safety minute in a grounding meeting than grounding? Well, I want to present Jerry's 3 rules for grounding. Grounding involves making a lot of assumptions. You're constantly assuming when you're doing grounding design. And so on that note, I have developed 3 rules for grounding. The first rule is always err on the side of safety. If you have to make an assumption, make that assumption in the safe direction. Once you've done that, minimize your over design. Is that you don't need 10 by 10 foot spacing in a lot of grids. It's probably safe, but you really don't need 10 by 10 foot spacing in grids. Then, once you have erred on the side of safety, or once you minimize over design, just make sure that you're still erring on the side of safety. So it's really all about erring on the side of safety, minimizing over design, and then making sure that you're still on the side of safety. So with that, let's get into a background on soil modeling. Fundamentally what we're doing here is we have to define the electrical properties of the soil in which the ground grid sits. Is that the ground grid is, pushing ground current back, ground fault current from the substation into the soil back to its source. So we are defining the electrical properties of the soil which the ground grid is pushing current into. And so everything we do with grounding depends on having a good soil model. So let's talk about that soil model. It's very important to grounding. The soil model just refers to different resistivities of soil at different depths below the surface. Soil resistivity, along with the surface area of the footprint of the grid, is going to be the primary driver of your grid resistance. Now, I have a formula for grid resistance. This is a rough formula for a solid plate, but this is kind of a formula that we use a lot in grounding design just to give a quick, dirty estimation of what we're expecting for a grid resistance. And it's not something you should really memorize per se, but just to show you, we have the resistance of this plate is equal to the resistivity divided by 4 times the square root of pi over the surface area of the footprint of the grid. And so what I want to demonstrate in this formula is that resistivity of the soil and surface area of the footprint is really critical to the overall resistance of the grounding system. Now, soil resistivity is critical because fundamentally, we've got this fault current, this ground fault current in the station, and it passes through the ground grid into that soil, through that grid to soil interface, on its way back to the source. And that soil has a resistance defined by the resistivity, and the current times the resistance, the ground fault current going through the soil times the resistance of the soil gives you that ground potential rise, which is the potential of your ground grid during a fault with respect to remote earth. So soil model is very important, central to the performance of your ground grid. Now, what is soil resistivity? Well, IEEE 81 gives us a definition of soil resistivity, which is fairly easy, straightforward. A measure of how much of a volume of soil will resist an electric current and is usually expressed in ohm meters. And so I see I put some equations here below that. Resistance is equal to resistivity, resistance through a conductor of length L is equal to resistivity times this length L over the cross-sectional area A of that conductor. Resistivity is equal to resistance times the cross-sectional area of the conductor divided by the length. Resistance is in ohms, resistivity is in ohm meters. This just gives you a conceptual understanding of what it is we're talking about in resistance versus resistivity. Now, Wenner 4-pin test, very important. You'll hear a lot about. This is actually how we measure the resistivity of the soil and how we come up with the model that we use in grounding. Now, Wenner 4-pin, there are multiple tests by which to measure resistivity, but we use Wenner 4-pin. There are some like Schlumberger, which have, which are much less labor intensive. You don't have to move all of the pins between tests. But during the Wenner 4-pin test, we like the Wenner is used because the Wenner provides better, more accurate results for resistivity at more shallow depths of the soil. And if you think about it, your ground grid is sitting, typically 1.5, 2 feet below the surface of the finished earth. And so that's really, that's going to have a tremendous impact on the performance of your grid. Yes, lower layers will as well, but those upper layer accuracy is very critical to predicting the performance of your ground grid, which is why we need that more labor-intensive Wenner 4-pin test. And basically what we do in the Wenner 4-pin test is we've got 4 probes, and they're equally spaced by a distance of A between them. And they're buried a distance, a length of, a depth of B beneath the surface. And we run current through them, through the outer pins, and then we measure the current, measure the voltage drop between the inner pins, and voltage divided by current gives us resistance. And so we have the resistance at varying A spacings of the of the probes here. And so this is what it looks like. And so now let's talk about, we've got resistance, but we really need to have resistivity, because resistivity is what we model in our grounding simulation software, that WinIGS, that CDIGS, we're modeling directly resistivity. So we measure resistance in the field, and since the meters see the current voltage, and then IEEE standard 80 presents 2 equations to convert the resistance measured by the Wenner 4-pin test into resistivity. And going to talk a little bit about these equations, further on in this presentation, because there are some important things. We see this equation for resistivity equals, a bunch of stuff. We've got A over B, A and B kind of pop up in different places. I'm not going to recite the equation verbally. You guys can all read it. But what we note here in equation 49 is that it depends on both A, which is the horizontal spacing between the probes, and B, which is the depth. Just to look back, this distance A and this distance B plays in equation 49. In equation 50, we have something that's much more, that's much simpler. I mean, if you do a mathematical exercise of just putting in, like infinity or a very large number into B, you'll see that this equation breaks down into this. So we have an approximation with equation 50. Now, equation 49 versus 50. 49 is going to provide a more accurate resistivity because it accounts for probe depths. 50 is something that's pretty easy to, quick and dirty to do if you're ever looking at, formulas and you want kind of a sanity check. I've provided a graph that shows differing results between equation 49 versus equation 50. Assuming a B of 1/2 foot for A spacings, a depth of 50 of 1/2 foot for horizontal spacings less than or equal to 10 feet, and 1 feet for horizontal spacings above 10 feet. When Commonwealth specifies resistivity traces, by the way, we specified this probe depth, and we'll talk a little bit more about that later, but this is something that we recommend. But as you can see, we can get differences of around 10% at these lower spacings of like 2 feet, which are representing where the grid is buried, versus next to no difference at spacings of 100 feet, and beyond. So this shows that equation 49 does provide some additional accuracy, and we'll talk a little bit about that more in future slides. Now, we've got all these little resistance numbers at differing spaces, because what you're going to do is you're going to take these, specify these over a horizontal trace. You're going to specify increasing A distances, maybe 2, 4, 6, 8, 10 feet, 20, 30, 50, up to 100 by 10, 100, 200, 300. You're going to specify these A spacings here. Then you're going to get these resistances at differing A spacings, and you have to put them into grounding software to create an actual model of your soil. So individual Wenner 4-pin readings will be taken at progressively increasing horizontal A spacings. Now, the key is that these A spacings resemble resistivity up to that depth. For example, an A spacing of 2 feet represents, resistivity down to 2 feet, whereas an A spacing of 200 feet represents resistivity down to 200 feet. Now it's, in side note, B spacing, that depth of the probes, should be a little less at narrow A spacings to avoid capacitance between the probes. Because we've got, two parallel conductors buried in a semiconductor, a dielectric of the soil, and there can be capacitive issues there. So we want to avoid going too deep. But we need to balance that with good probe to soil contact, which is something we'll talk a lot about in lessons learned. But you get a little bit further out, you can go down to a foot. Field crews don't like to go too deep, by the way, because that means hammering the probes in and pulling that out. If you got, you might, 5 foot at 5 foot depth at 300-foot spacing might sound nice, but your field crew is not going to really like to, pull them in and out like that. So basically, we've got all these different readings at different horizontal A spacings, and we're going to enter those readings into the CDEGS RESAP module or into WinIGS, or two major grounding software we work with at Commonwealth. And then we're going to create a model of varying numbers of layers of resistivity at different depths, 100 ohm meters down to 10 feet, 200 ohm meters below 10 feet, for example. In the field, and again, this is key, is that the field readings provide resistivity down to a certain depth, but the grounding software converts this to readings at certain depth. So, that's a big important, one of the important things that grounding software does. Sometimes grounding software will ignore the depth. We don't recommend that. Again, we'll talk more about that later. A lot of times, 2 layers of soil are going to be enough to represent your soil. Resistivity down to a certain depth, and then a resistivity below that. Now you have to use your judgment, looking at the soil boring samples, looking at curve fittings to individual Wenner readings to determine if more layers are necessary. And we're going to talk a lot about that judgment down the road here in this presentation. Now, another thing to be careful of course, is that high resistivity at upper layers are going to increase tolerable touch and step voltages, but soil at upper layers might be removed during construction. So that means just use some judgment as to how you account for those upper layers. So grounding software. Here's a picture of WinIGS's soil model, soil modeling tool. Traces are going to be your individual readings are going to all be entered into one window, and unfortunately it can't select and deselect between traces easily. Now, the program will compute up to 3 layers of soil from the Wenner 4-pin, and it can accept up to 4 layers, up to a 4-layer model, computed in a separate source, such as CDEGS RESAP. We have actually done grounding studies at Commonwealth that are so complex that we felt that WinIGS, for example, did better modeling of the surrounding network, whereas CDEGS created a soil model that was more believable relative to the boring samples. So that's sometimes you can get involved in something like that. Now let's look at CDEGS. The traces are all entered separately, which is really nice because that allows you to select or deselect traces. Maybe I've done a project where I noted that one trace was parallel to a distribution line, and I didn't really like that trace, and so didn't seem seemed a little bit low, and so I eliminated that trace and got a soil model that I was more comfortable with. So eliminating and selecting and deselecting traces, big advantage of CDEGS. CDEGS has a frozen soil model simulation. Some organizations like that frozen soil simulation better than other organizations. CDEGS can also create a soil model with many, many layers. Now, having many layers is going to provide a more accurate soil model, but it's also going to drastically increase your computation time. If you've done early on, I've done did a frozen soil simulation with many I think it was maybe about 5 layers I did, and each one of those runs took about 45 minutes, which was not incredibly fun to have to deal with. So adding layers adds more computation time. Now, fitting that curve. How well does the computed soil model match the measured soil data? Most of the time you're going to find that 2 layers are adequate. And here I show a screenshot of CDEG's results where 2 layers really are adequate. Just walking through what we see here, we see these blue dots are individual readings. They're reasonably close to one another throughout. And we've got this green curve here, which is the model that CDEGS computes of the soil overall. And then we've got this purple, kind of staircase curve, which is the model that CDEGS recommends to use in your grounding design. You can also see that RMS error here is 10.8%, 10.84%, very low RMS error. This is a great soil model. 2 layers are fine for this, higher layer above a lower layer. Sometimes, you might have a lower layer versus a higher layer. In this case, it's a little interesting here. A little perk of CDEGS is that this last little dot right here is not actually a measurement. It's just the end of the CDEGS curve. CDEGS puts that in, and it's a little tricky, but that's not an actual measurement. We've got these individual measurements get higher as the A spacing increases. More A spacing and represents more greater depth of soil. And we can see that this green curve is fitting the data really well. We've got an RMS error of 9.6%, so that's pretty nice. And then CDEGS makes kind of a big jump at this depth, but they've got a lot of soil analytics built into their software, and they predict what the layer is, and most of the time, and you have to think critically about these, and does this match your soil data and whatnot. But we've seen that we go to a much higher level of resistivity below. Now, sometimes you do need 3 layers. We can see 2 examples here. We've got a couple of they're kind of bell-looking curves. We have layers that it gets a little lower as it goes down, and after getting lower it goes back up, gets low, gets high, gets low. And we can see that in these cases 3 layers are really justified for the data. So that is examples of where 3 layers are appropriate. Curve fitting. Sometimes grounding software is not perfect. Wenner 4-pin readings, even done completely to the desires of Commonwealth Associates, are not perfect. And sometimes, you have to sift through data and kind of compensate and make do with what you have. And this is a poorly fitting curve. This is a couple of things to look at. We've got an RMS error of 84%. That's pretty big. We've got we've got data kind of readings speckled all over the place here. And then we've got this little outline reading here. It's really low. I mean, this little, especially like a lower outlier, that's really concerning if that's going to bring the rest of your model down. And, who knows, what kind of, maybe there was a mistake in the field that made this. So this is really a model that, I would not want to use for grounding design. What we would do is we would select combinations of individual traces. We would look for that RMS error to lower to fit the curve. We would try to we would look for numbers that were conservative. We would look for numbers that were at the upper end of what we would expect based on soil boring reports. And believe me, we're going to talk in depth about, expectations based on soil boring reports, because that's really critical to good grounding design. But that's what we would do for this, for such a poor curve fit. So this is not something we would use. Now let's go to the next slide. Look at this backling of data. Can anybody tell me if this is good curve fitting or not? Is this good usable data? Anybody? Well, not hearing anybody.
We got 2 no's, 3 no's, 4 no's in the chat.
Okay.
Nice.
Yeah, this is absolutely, this is actually good curve fitting. That the key is that, the RMS error is very low, that this is a logarithmic graph. And so this is not over this is the number, the range that this is actually a relatively low range. So even though it looks bad, it's just because of how the data's fit. This is actually data that I would use for grounding. So, low errors. All right, so let's talk about picking good traces. You have to find enough Wenner spacing for ideally the diagonal width of a station. Remember that we need three times the 3 times the space for 4 probes, because we've got 4 probes with 3 times the spacing between them. So if you're wanting to go up to, say 200 feet, you really need a track of 600 feet to measure that off of. You need to look for similar soil. Be at the site if you can. If not, look for something very similar. Just if you're on a hill above a river, don't go below that hill into the river, next to the river, to take your measurements. And don't go into a swamp. Don't go into a junkyard that maybe has you know contaminants in the soil. So look for similar soil. Uh, Very important thing is look for obstacles. Power lines are going to induce voltage in long leads, and they will also induce current in long leads, and that can jeopardize both not only the accuracy of your readings, but also safety of the crews taking the measurements of these Wenner 4-pin tests. Also, there's things like pipelines, railroad tracks, metal fences. What's going to happen is the meter is injecting current. That current is going to be picked up by the pipeline, picked up by the railroad tracks, dropped off at the next probe, and the meter will not know that there is a pipeline there picking up the current, and will think that the soil is better than it actually is. Another thing that does the same thing is an existing substation with metal infrastructure, like an existing ground grid. The existing ground grid will pick it up. Just this last week, I had to reject some soil measurements because they were taken within about 10 feet of parallel to an existing substation with an existing ground grid. And sure enough, those soil models, the soil numbers looked a lot better than I was expecting based on the boring reports. So, never do that, parallel to an existing metal infrastructure like a railroad pipeline or existing ground grid. Generally, orient the traces perpendicular to these obstacles. Uh, Important to have an idea of what to expect. Farm country, you see farm fields, there's usually a lot of mineral-rich soil where farm is, minerals, lower resistivity. You can expect, good soil. When we're building data centers around Columbus, Ohio, and Indiana, these large footprints in farm fields with very good soil resistivities. Those particular ones have been very straightforward to ground. Salt water nearby. If salt water is nearby, it's going to seep underground. Rain, mist will come off and leave salt in the ground. That will be very low resistivity. The best soil I've encountered in my career was actually near the Gulf of Mexico in Texas, where just a couple miles away from the saltwater Gulf. Is there a flood basin? Desert can be a little tricky because usually, something that's dry and sandy would be very high resistivity. But actually what happens is that mineral-rich groundwater evaporates through the soil and leaves minerals there. And because it doesn't rain, the minerals are not washed away. So you can actually get some low resistivities sometimes in the desert. Now, areas with lots of shallow bedrock, they're going to have high resistivity. Rocky soil, they're going to have high resistivity. So that's something to be aware of. Now, here's a picture. Here's a chart from IEEE 80 of different soil resistivity ranges. Wet, very wet organic soil will be 10 ohm meters. Moist soil will tend to be 100 ohm meters, dry soil 1,000, bedrock 10,000. Now there's differing soil types that we'll talk about in a little bit that you can Google and get more typical soil resistivity ranges for different types. We do not have the copyright for that information, so I did not put that into this presentation, but it's very easy to Google and find typical values for typical soil types. So on that note, let's talk about soil reports, the anatomy of them, and things to look for. They're called boring reports, and they describe soil types found in boring samples. That the soil, the geotechnical subcontractor will go in and take boring measurements, maybe 20, 40 feet down. They'll drill out and they'll bring and they will take the soil to the lab and they'll evaluate the moisture content. They'll evaluate the soil types found, and they will put that into a nice chart that I'll show you an example of in a little bit. They're going to do Wenner 4-pin resistivity measurements. Be careful of the date that they were taken, and observe the date that they were taken, and observe the conditions that they see when they were taken. They were another important thing to look for is the mapped locations of Wenner traces in the boring samples. In the Wenner traces, look for obvious sources of interference. Is that when I saw the picture of Wenner traces that were right next to the fence of an existing soil of an existing substation, that immediately set off my radar, my alarm bells, and surely enough, the numbers did not look good. Also, look for how close they are to the actual site. A lot of times, we've done a lot of work for solar farms lately, and you'll find that they've got resistivity traces over many, many parts of a many-acre solar farm. So some of the resistivity traces are not going to be so relevant because they're far enough from the substation site. So pay attention to where those actually are. Now, good Wenner 4-pin reporting from the field. Wenner 4-pin test results from the field should include probe A spacing, that horizontal spacing. They need to have that, but they should also include the probe depth. Include the resistance and the resistivity, accounting for B depth, meaning that use equation 49, not equation 50, because it's more accurate at the lower depths that the probe that the ground grid is buried at. Now, the equation 49 derived resistivity will help you judge the soil at a glance. You'll be able to look at it at a glance and see, what this soil is going to be like. We should, take note of the meter used. Should talk about, ground cover conditions and soil conditions observed. It should talk about weather conditions observed. Did it rain recently? What time of year was it? Things like that. Now, poor reporting from the field could just be a spacing in resistivity. You can enter that into the software, but what you cannot do is as easily judge the quality of the measurements. Poor reporting will provide you just enough information to enter into the software. Good reporting will provide you, the grounding engineer, with enough information to judge the accuracy of the results. And I can tell you that as the subject matter expert at Commonwealth Associates for grounding, we will not put out a grounding study that we do not understand the soil at the site. That we will not just put numbers into the software and accept whatever the software puts out. That we make sure that the numbers that we are using make sense as to our understanding of the site. So that is very critical to grounding software, to grounding design, to ensure that the safety of your grounding system, that it adheres to safe thresholds. We have to make sure that the soil model that we are using makes sense. And the key is with Wenner 4-pin reporting from the field is to ensure that we have enough information to judge the quality of those measurements. So here's a very important slide. It's an example of a boring report. It was, and what we see here is we see, soil depths at different soil types at different depths. It's that we're going down. We've gone into the field with the drill, taken out, soil, a soil sample in up to about 20 feet. Boring terminated at 20 feet. It's been taken to the lab, and it's been analyzed as to what kind of soil we're seeing. We're seeing about 3 feet of poorly graded sand with silt, SPSM, clayey sand, SC, from about 3 feet down to 12 feet, silty sand from about 12 down to 17, and then elastosilt with sand. And again, you can Google these SPSMs, these abbreviations, which we'll talk about next slide. We see that about 12 feet we encountered groundwater. And so, we're noting the soil types, noting groundwater. Now, about those soil types. The types of soil are defined by the Universal Soil Classification System. It was developed by Harvard professor Arthur Casagrande in the 1940s. It was actually in the height of World War II. They were trying to figure out how to quickly assess soil to put airfields in places that they had just taken. So that's where the Unified Soil Classification System came from. The types of soil are going to be documented at different depths on the charts describing the samples of borings, and that's just what we saw. And key, this is one of the most important pieces of information to validate the resistivity results relative to the boring samples. It's the soil types. I was just looking at that soil type at different depths. Does that does the model that you're getting out of CDAGS when IGS, does that seem reasonable relative to the soil types that you're seeing? And of course, those different soil types are going to have different two-letter group symbols. And again, you can Google to find that range. Commonwealth doesn't own this copyright to that information, which is why I'm not showing charts here. But CH is fat clays. That's going to be around 10 to 50 ohm meters, for example. SC is clay sands. It's going to be 50 to 200 ohm meters. This is how you judge soil boring reports. So another key chart that I want to show is from IEEE 80, figure 17. This is not something that you could do quantitative analysis on per se. This is just a sample for sandy loam, but it shows you some important concepts in soil here. Is that we see this curve 3, which represents the temperature of the soil. This curve 2 represents the percent moisture content. Curve 1 represents the percent salt content. We can see that as as the soil becomes saltier, warmer, and more moist, that the resistivity drops down. We can see this drop right here and for the temperature curve, which occurs right when it starts to freeze. So that's a important concept here in just to conceptually understand how salt content, moisture content, and temperature affect the resistivity of soil. So with that, we're going to go to a quick lessons learned, and we don't want to pick on anybody in particular. I've tried to delete any identifying information from this, because we've seen, we have issues regularly from measurements that we're given all over the place, and different as part of our job is to look at these very carefully and ask difficult questions, because anything that if we're not completely confident in our soil, then anything we do downstream is going to be of little value. So this is not to pick on anybody, but just to show some lessons learned. So something I loved about this soil boring report is that it had this really wonderful chart where it showed all the different boring samples with different soil types, and where the groundwater was encountered, so you could compare across the area how these different what soils types occurred at different spots. So this was kudos to whoever did that. This was a wonderful figure. Please, if anybody does a soil boring report, put a figure like this in here. Now, the problem is, though, well, B1 and B2, we looked at them because they were close to the substation. We see a little difference up top, but definitely similar stuff below, which you'll see less variation below than you do up top. But what we see here is we're seeing lean clay is going to be about 25 to 60 ohm meters. Sandy clay is 50 to 200 ohm meters, and then this MH elastic silt is 80 to 300. So, okay, so we want to be conservative here. We want to go a little bit on the upper end here. And so let's say that a typical model we expect would maybe be about 3 to 5 feet of maybe 100, 200 ohm meters above, above 300 ohm meters. So what did we get? And then, of course, noting the groundwater, that groundwater is present. So what did we get? Well, they gave us these resistivities in ohm centimeters. So we're looking at this, and that's, we can see what we're seeing at different heights, and we're seeing resistivities in the thousands. I mean, we're expecting maybe 200 at 5 feet over 300. Conservatively, that would be the upper end of what I would expect. And we're seeing readings in the 3,000s on all of these, that's, so this is, just, so we're really, so this is way off of what I'm expecting. Well, does anybody see a comment in here that just jumps out right away? Anybody entering anything into the chat, Dell, that something that jumps out right away? Well, what we had here
Yeah, we got
was,
one comment so far. It says the comment is 1,750 ohms at 1 foot spacing. That's a
yeah,
comment.
well, that is definitely a number that pops the eye. So that was what set off my radar screen, just relative to our boring reports. But what really jumped
Also,
out at it, oh, sorry,
another
go ahead.
comment too is just check in temperature. Is that in Fahrenheit or Celsius?
That is a good question. I'm gonna guess it's probably in Celsius Fahrenheit because it's November, and just knowing what was typical for where
Yep.
these came from. I don't want to
And one
say
more
where.
comment is Jeffrey Watson mentioned recently mulched.
Got it. That was the issue. All these readings included this comment, recently mulched. What does mulch look like in your yard? It's little chips of wood, little chips of dirt, chips of organic matter, little chips of chippy soil. What is that like if you're putting a probe into chippy soil and it's making, what kind of contact is that probe making with the surrounding soil? Well, it was not making good contact. And so we specified that they clear the area and do a little bit of clearing, and subsequent soil measurements came back agreeing with the boring reports. Now, so that's really good, is, taking, getting that good, soil, being careful that you're actually getting good contact with the probes. Another one we had was inadequate probe depth. We were given the soil results for a station in sandy soil in inland Florida, and we expected high resistivities because it was sand and inland, but resistivities like this, 53, 5,000, 6,000, 8,000, 9,000. It was just, it was similar throughout. It was in the resistivities were in the, above the five, like 5 to 10,000 ohm meters. So um, what jumped out at us was these shallow depths, is that these depths of 0.3 inches. That's not very deep. And so particularly in the sandy soil, you will have a little bit lesser contact uh, with the probe and your um, in the surrounding soil. And so we ultimately requested that they that they go back, and we don't really need spacings at, a half a foot, because that soil is going to be disturbed to a point during construction that it's really not worth it to measure. So we usually specify it beginning at 2 feet. We like to have at least 6 inches of depth from 2 feet to 10 feet, and then above 10 feet, we'd like 12 inches. So that was really the issue there, was using these very low probe depths. Um, so that was what we dealt with there. So other locations had better results, interestingly, more believable numbers, because their soil, even though they had the low depths, their soil has had more clay in it, and so the soil was able to make, the probe was able to make better contact with soil that was less sandy. So you'll just really, if there's one takeaway from both of these examples, it's just be cognizant of conditions that can really impact the contact that the probe is making with the surrounding soil, because the meter just reads what it reads, and it doesn't know if that resistance is coming from, it doesn't know if the high resistance is coming from bad contact with the soil, or if the soil is really that bad. It doesn't know if the current's being picked up by a parallel pipeline, or if the soil is really that good. The meter just reads what the meter reads, and it's up to the people doing the grounding design and taking the measurements to make sure that it's reading good information. So best practices for PMs and project leads. Engage your grounding SME early on when traces and when or 4-pin resistivity testing parameters are specified. In Commonwealth, if you're working with Commonwealth on your project, we can provide specifications for ordering Wenner 4-pin tests to customers. We can specify traces, specify methodologies, things to look for, things to, so that you don't have to have a retake, kind of put our painful lessons learned into a document that will specify, that will make sure that you're taking good measurements. Have resistivity measurements taken and provided to the grounding team as early as possible. This gives the project team time in case mistakes are identified in the traces. And also have the boring reports ready with adequate time for the grounding SME to compare them to the resistivity measurements. Because again, Commonwealth Associates is not going to put out a grounding design where we are not confident in our soil model. And that, usually means they're looking at boring reports and making sure it makes sense relative to what we are, that the numbers, make sense relative to what we're expecting. So with that, let's go into conclusions. An accurate soil model with varying resistivities at varying depths is critical for grounding. Soil models are created by taking Wenner 4-pin readings in the field and entering them into WinIGS or CDEG's grounding software. Soil models begin with good traces, those lines on which the Wenner 4-pin measurements are taken at increasing horizontal spacing. And they should be as close to the site as possible, but avoid things like power lines, parallel metal structures that might throw them off. To evaluate your Wenner readings, compare the resistivities to typical values of the soil types observed in boring reports. Look for things like groundwater or anything that might lead to probe the soil contact. If you have bad readings, maybe they can be addressed by using a higher current meter, looking for obstacles like parallel metal or power lines, improving probe to soil contact. You might inject soil, salt water around the probes, clear brush and debris around them. And engage your grounding SME before ordering the Wenner 4-pin tests, just so that you can make sure that you are, head off any issues and learn from the grounding SME's experience. And finally, grounding is all about so many assumptions you have to make, but always err on the side of safety. So with that, I would be happy to take questions.
If you guys have a question, please put it in the chat and I will ask it for Jerry to answer. And while we're waiting, I think we had another one that came in. So assuming a higher resistivity for soil is always safe, conservative option, right? So do we always assume that higher resistivity is safer, or is lower resistivity safer, Jerry?
Well, it is actually not always always safer to assume a higher resistivity because you can have a situation where you might have a very high resistivity upper depth in a lower resistivity above that. In the higher, of you have a very high resistivity at higher depths, that will that will basically act like an insulating layer. It will protect personnel, kind of similar to we have a couple of inches of gravel that help protect personnel. That could actually function similarly to the gravel in make uh, part of grounding analysis is we compute a voltage that people can experience through touch and step phenomena, which is kind of a different different subject. But we compute tolerable levels, and so if you have an unrealistically high thin upper layer of current of soil, that could actually give you an unrealistically high tolerable voltage. So the answer is no, that tolerable um, that a higher that higher resistivity soil is not always the most conservative.
Okay, thank you for that, Jerry. Another question is coming in. When it comes to RMS error, what percentage should we look for when we need to add another layer? Above 15%?
This directive came out of the CDEX users group, which we are not part of, but I believe the directive was either 15 or 20%. The directive was not to use RMS error above 20%, I believe was the number. And this really, when you're finding that you have too high of an error, Commonwealth does not take that as gospel, but you really need to, it's a warning sign, and you really need to look at what's going on. And if you have some outlying measurements, if you have some traces that are maybe a little unrealistic, we kind of go through and we deselect traces and look at what ultimately looking at the higher end of what makes sense. And you can really and again, being careful not to have a very high upper layer like I just talked about in the previous question, but really going through and looking at, and sometimes you just need to put it into like an outline of your grid and see what gives you the highest resistance. But really looking and seeing what makes sense. So the CDEX users group recommends not to use something above 20%. Our practice is that above 20% is a warning, and then just go from there and try to get the conservative end of something that makes sense relative to boring reports.
Okay, I think we have time for one last question. So, last question. Do certain soil types make a site unsuitable for building a substation? Or is the soil always tested first so that grounding system can be designed to suit the conditions?
Well, I don't think that they necessarily, I don't think it's often considered the grounding implications of certain soil types, but there are certainly other structural considerations that might make a site unsuitable. And that's really, I'm an electrical engineer, and I've not really dove into the civil engineering side of that, but we certainly have very talented civil engineers at Commonwealth that look at that and are well aware of that. So if you're ever interested in learning more about that, feel free to reach out to me, and I can put you in contact with people that can speak very skillfully to that.
So, Jerry, maybe to follow up on that question, I think maybe the question was aimed at is there a situation where we can't ground out a substation? Is there a soil so bad or so unfavorable that we really have to look at a different location for a station? Have we ever seen anything like that?
I'd never seen a location be eliminated on that criteria, but there are some locations that are so bad that we might need to do something drastic, like, for example, bring in what's called ground enhancing material, where we will actually bring in lower resistivity material and put it around the conductors that are buried. There are things that you can do to maybe add, getting into split factor, which is a whole different subject, as you can certainly add, counterpoise going out, which is basically uh, connecting a cable from the ground to grounded poles going out. So probably the first thing you would look at in that situation is a ground enhancing material. So I've never seen a site eliminated on that criteria, but there are some sites that are just so bad that you need to do something drastic for them.
All right. Well, wanted to thank everybody for attending today. Thank you very much for your comments. Thank you for your participation. And thank you very much, Jerry, for this enlightening conversation and topic. So, all right. So we will be reaching out with our next presentation, which will be November 20th. I hope you guys can all make it. Please email the email here at the beginning of the slide, marketing@cai-engr.com for PDHs. And we'll make sure you guys get credit for those looking for PDHs. And we'll see you next time.